After learning about volumes of revolution and surface area of revolution, and after being able to evaluate improper integrals, a really interesting example is called Gabriel's horn. So if we are looking at the given function f of x equals 1 over x when x values are greater than or equal to 1, this is going to have us try to find the volume of the solid created when rotating that region about the x-axis and the surface area of revolution of the solid created when rotating that curve about the x-axis. So here is a visualization. I have the function 1 over x, but only when x values are greater than or equal to 1. So we have this curve that is approaching the x-axis here. And so we're looking at it forever as x values go to infinity. And we're thinking about the volume of the solid created and then the surface area of that solid created, the surface area of revolution. And so we'll go ahead and try to find each of them one at a time. So let's start by finding the volume of the solid. So here the volume of the solid is obtained by doing the integral from 1 to infinity. And then the cross sections are going to be circles. So we're looking at pi r squared dx, but what is that r? What is that radius here? So if I just take a sample cross section at x, so that cross section again is going to be a circle, and the radius r is going to be just 1 over x. So we're going to have 1 over x as my big radius squared. So let's go ahead and pull a pi out of there. So we'll have pi, the integral from 1 to infinity of 1 over x squared dx. So this is an improper integral. We'll write it as a limit. So we'll leave the pi in front. We'll put the limit as t approaches infinity, the integral from 1 to t, and I'll rewrite 1 over x squared as x to the negative 2 dx. So now I have pi, the limit as t approaches infinity. The antiderivative of x to the negative 2 is x to the negative 1 over negative 1, or negative 1 over x, evaluated from 1 to t. And then I'll go ahead and move my work up here. So we have pi times the limit as t approaches infinity of negative 1 over t minus negative 1 over 1. And so as t approaches infinity, negative 1 over t is going to go to 0. So I have 1 over a really big number. That first quantity is going to 0, and then minus a negative 1 is plus 1. So this whole limit is just 1 times this pi in front. So I end up with an answer of just pi. So the volume of the solid created when we rotate this region, so we have this region underneath 1 over x from 1 to infinity, it turns out if I find the volume of this solid, it has a finite volume, right? Even though this is going all the way to infinity. So now let's take a look at part B. To find the surface area of revolution, we're going to start with the integral from 1 to infinity of 2 pi, and then the radius is 1 over x, so 2 pi times 1 over x, and then I'm going to need the square root of 1 plus the derivative of 1 over x squared. So again, my function was y equals 1 over x, or x to the negative 1, so y prime is negative x to the negative 2, or negative 1 over x squared. So we'll put negative 1 over x squared in here. And so we have the integral from 1 to infinity of 2 pi, and then I have 1 over x on the outside, and then the square root of 1 plus 1 over x to the 4th dx. Now, looking at this problem, it doesn't have a clear integration strategy when you look right at it. It's not like, oh, this is just a quick whatever. So let's go ahead and try to think of a different way to determine whether this improper integral converges or diverges. And so what I want us to notice here is this 1 over x, and this part here, the square root of 1 plus 1 over x to the fourth piece. So the square root of 1 plus 1 over x to the fourth, I hope we can convince ourselves that that's a positive quantity. And so what I'm going to do here is set up a comparison. So I'm going to try to compare this to 1 over x dx. And we know the integral of 1 over x dx from 1 to infinity, of course, is an improper integral that diverges. So this is a quick one, right? We can actually even just do this one off to the side. You know, we could turn it into a quick limit as t approaches infinity, the integral from 1 to t of 1 over x dx. The antiderivative is natural log from 1 to t, and then the natural log of t minus the natural log of 1. As t goes to infinity, natural log of t goes to infinity. So this diverges, right? So we can quickly show that, or again, that's something that we should have in our back pocket and know that the integral from 1 to infinity of 1 over x dx diverges. Well, over here, how does this compare? Well, this is multiplied by 2 pi and multiplied by this positive quantity here. So this is definitely bigger, right? So I know that the integral from 1 to infinity of 1 over x diverges, right? We can show it, or we should definitely know that this is the case. And so this whole thing is definitely bigger than that. So if I'm bigger than something that diverges, this must also diverge. So this diverges, this whole quantity ends up being infinity. So now, why is this an interesting problem? Well, in part A, we found that the volume was pi. So this Gabriel's horn has a finite volume. But in part B, we found that it has an infinite surface area. So this is called Gabriel's horn. It's a famous paradox. Sometimes it's also called the painter's paradox. So if you try to paint the outside of the surface of the horn, you would need an infinite amount of paint. But for some reason, you can fill it with a finite amount of paint. You can fill it with pi cubic units of paint. So this is something that should definitely blow your mind. Really interesting type of problem that we can study now that we know volume, surface area of revolution, and can evaluate improper integrals. And if you were interested in rigorously solving this without the comparison theorem, I would challenge you to do so. And the hint that I would give you is a trig sub.